Today we want to finish up looking at approximating definite integrals since we got into this yesterday, and now we have to just keep going. Past halfway, so keep on going. In the first category, we have approximation methods where we assume that the function is constant for each delta x. And this encompasses left, right, and midpoint rules. So we're imagining that we're just flattening out the function and using the area of a rectangle, length times width, on each delta x. So we either use the left endpoint and go straight across, or the right endpoint, go straight across, or the midpoint and flatten out to make rectangles. Left and right end up on either side of the actual value if the function is always increasing or always decreasing. And so it makes sense to try to average those. What we found is that averaging the left and right will give us the trapezoidal rule. And under that assumption, we're assuming that the function is linear on each subinterval. So the trapezoidal rule is the average of the left and the right. And this makes sense because a trapezoid is just the average of the rectangles that contain it. That's the 1/2 base times height. So we use left endpoint, or we flatten it out with right endpoint. And the trapezoidal rule will be the average of those two rectangles. So in this case, we're assuming that f of x is linear by just connecting the left value and the right value with a line. Sitting above, going beyond midpoint and trapezoidal rule, we can assume that f of x is quadratic. And this results in Simpson's rule. Where the Simpson's rule is a weighted average of the midpoint rule and the trapezoidal rule. It's a weighted average of 2 midpoint rules and 1 trapezoidal rule. So Simpson's rule, simp n, is going to be 2 midpoint rules plus 1 trapezoidal rule, all divided by 3. So the midpoint rule and the trapezoidal rule, in general, one will be an overestimate and the other will be an underestimate. Where left and right decide what side they're on, based on whether the function is increasing or decreasing, the midpoint rule and the trapezoidal rule decide what side of the actual value they're on, based on the concavity of the function. And what Simpson noticed is that the difference between the actual value and the trapezoidal rule was about twice as much as the difference between the actual value and the midpoint rule. So he said, we will make an average, but we're going to count the midpoint rule twice since it tends to be closer. All right. So, and they all fit into nice little convenient boxes. We can assume that the function is constant. We can assume that the function is linear. We can assume that the function is quadratic. What we notice is that when I say left and right go together, if a function is increasing, then the left endpoint will be an underestimate, and the right endpoint will be approximation will be an overestimate. When the function is increasing, then the left approximation is an underestimate of the actual value of the definite integral. And the right endpoint approximation is an overestimate. If the function is decreasing, then switch them around. The left will be an overestimate. This makes sense. If the function is increasing and we use the left endpoint, that's where the function is lowest on the interval. And so the function is increasing after that. The midpoint rule and the trapezoidal rule will also be on opposite sides of the actual value, but this will be based on the concavity of the function. If f of x is concave up, then the midpoint rule and the trapezoidal rule will be on opposites. So, and we'll make this decision based on the concavity. So if we draw a function that's concave up, we draw a function concave up. Oops. I didn't want that extra hook there. I just wanted concave up. If we imagine a function that's concave up between two values, we can see that if we connect these with a straight line, we're going to have an overestimate. So if I connect these two values with a straight line, we can see that the trapezoidal rule, which puts a straight line between those two, is going to be an overestimate. This is whether the function is increasing or decreasing. If I have a function that's decreasing in concave up, the trapezoidal rule still overestimates. So whether the function is increasing or decreasing, the trapezoidal rule is an overestimate. But if it's concave up, if the function is concave up, then the trapezoidal rule will be an overestimate. So if I have a function that's concave down, if I have a function that's concave down, the trapezoidal rule will underestimate. Any questions? So I pick the, I happen to know that the midpoint rule and the trapezoidal rule are on opposite sides of the actual value. And I choose to draw a picture for the trapezoidal rule, showing that the trapezoidal rule overestimates when the function is increasing or decreasing, but it's concave up. And the trapezoidal rule underestimates when the function is concave down. And right now, you're taking my word for it that the midpoint rule will underestimate when the function is concave up. So we can make a similar style argument for why the midpoint rule is going to underestimate when the function is concave up. And when I say we, I mean y'all. So that is an open question I'd like you all to think about over the weekend. How can we make an argument? How can we convince people that the midpoint rule is going to underestimate when a function is concave up? It's easy to draw with the trapezoidal rule. It's a little trickier with the midpoint rule. We have to think about things. But the important thing is that the midpoint rule and the trapezoidal rule will find themselves on opposite sides of the actual value of the definite integral. Unless we disingenuously pick our midpoints to be very misleading. As usual, if we cherry pick our data, then we could make things look bad. So don't cherry pick your data. But since the midpoint rule and the trapezoidal rule will be on opposite sides of the actual value of the definite integral, it makes sense to find an average. But what we observed in Simpson's rule, it shouldn't be treated like both sides should not be treated equally. The midpoint rule tends to be better, so it makes more sense to make a weighted average of 2 midpoint rules and 1 trapezoidal rule to average those out. It also fits very neatly, since doing this means that we're assuming that f of x is quadratic on each interval. So it fits better if we do that 2 midpoint rules and a trapezoidal rule. It's more than just the actual values, that the trapezoidal rule is usually twice as far, because none of those things are really hardcore set in concrete. It's always exactly twice as far in all scenarios. It's just based on observation. Really, Simpson's rule comes from the fact that we can assume the function is quadratic on each subinterval, and this is what we get. Any questions? How's everybody okay? All right. One more thing to say about this approximating definite integrals. We know that if we use an infinite number of rectangles, then we should get the exact value. So the question becomes, how much more effort is needed to get more decimal places of accuracy? So to summarize, if we're using left and right endpoint approximations, and we do 10 times the number of rectangles, then we get 1 decimal place of accuracy. So using left and right approximations, if we want 1 more decimal place of accuracy, then we need to do 10 times the calculations. So if the left and right are within 10 of each other, and we need them to be within 1 of each other, we need to use 10n rectangles. If 5 rectangles puts left and right within 100 units of each other, then 50 rectangles puts us within 10 units, left and right within 10 units of each other. 10 times the number of rectangles for 1 more decimal place of accuracy. If we use the midpoint rule and the trapezoidal rule, with the midpoint rule and the trapezoidal rule, if we do 10 times the number of calculations, we'll get 2 decimal places of accuracy. So switching from 2 rectangles like we did yesterday to 20 rectangles would mean, instead of our approximations being 50 units apart, they would be going down 2 spaces to 5 to 0.5. They'd be within 0.5 of each other. 10 times the amount of work buys us 2 decimal places of accuracy. That's a lot. And when we average these two together, make a weighted average of these two and use Simpson's rule, 10 times the amount of work gets us 4 decimal places of accuracy, which is a lot. So we go from 0.5 to point, I wouldn't be able to come up with one. I'd lose track of what numbers I'm writing. 10 times the work gets us 1 decimal place of accuracy with left and right, 2 decimal places of accuracy with midpoint rule and trapezoidal rule, and 4 decimal places of accuracy with Simpson's rule. So if your left and right are within 1, but your tolerance is 0.1, you have to do 10 times the amount of accuracy, 10 times the number of calculations. If your left or right are within 1 and your tolerance is 0.01, you have to do 100 times the number of calculations. Any questions? All right, let's pause the video here and talk about next steps.